about or around ordinary points. Okay, by now you should familiar with ordinary, analytic, okay, point. Okay, so all this one we have learned how to find series solution around ordinary point. Okay, later on. Okay, later on, I will uh, um, I will brief you, I will explain to you how to find series solution um, uh, around singular point. Okay, around singular point or around singular point. So I will continue with example 6. Okay, I think I have given this for your task, but never mind. I will explain in detail today. All right. So find a series solution around x not equal to 0. This is example 6. Okay. For this second order homogeneous linear second order ODE. But again, okay, so the solution, we assume the solution will be in this form. Okay, in this series form, Cn x minus x naught power of n. Because x naught is equal to 0, and that's why it's reduced to Cn x power of n. Summation n from 0 up till infinity, Cn x power of n, because x naught is equal to 0. Okay, when you replace x naught with 0 here, that's why you have x there. Okay, but x naught not always equal to 0. There are some cases when x naught equal to 1, minus 1, and so on. Okay, so when x equal to when x naught is equal minus 1, so here you will be x plus 1. Okay, why x plus 1? Because x minus 1 will be x plus 1. Okay, when x equal to 1 here, then it will be x minus 1, because x minus x naught. Okay, so you just replace whatever x, the given x naught in the power series. So y equal to summation n from 0 up till infinity Cn x of n. Our task now is to find the coefficient of Cn. Okay, that is our main aim. Okay, to find the coefficient of Cn. Okay, so here we have y double primes. So in order to get y double prime, we need to get y prime first. Okay, y primes equal to, you differentiate y respect to x. So you have n Cn x minus 1, but now n start with 1. Okay, n can start with 0 as well, but then when n equal to 0, this term will goes to 0. Okay, when n equal to 0, that means 0 times something will equal to 0. That's why n start with 1. For y double prime, we differentiate y prime. Okay, so n times n minus 1, you bring the power down. Okay, so Cn x times x n power of minus x power of n minus 2. Okay, and then you replace this y primes with this y double prime with this series, and y with this series. Okay, so we get this. Okay, we will get this, and then the next step. Okay, we want to, okay, now the next step, this is the same step as this. In this one, it can be deleted. Okay, the next step, because we have x times y. Okay, so we replace here, we have minus x, okay, times y. You replace with the infinite series, and then you got to bring this y inside. So this x, bring this x inside. Okay, because x is independent variable. Okay, bring x inside. So that's why I mean x times x power of n will give you x power of n plus 1. Okay, that is the first step. Okay, so now the next step, okay, compare the power of x. Okay, here is x power of n minus 2. So in this series, x to the power of n plus 1. Okay, so you have to decide, okay, which power that you want to reduce to. Okay, because otherwise we cannot combine these two series. Okay, in the first example here, I reduce both, not reduce, I change. Okay, I change both power to x power of n. So I change this xn minus 2 to the power of n. The same here, I reduce xn plus 1 to x power of n. Meaning that in order to do that, this n in the first series, you replace with n plus 2. While in the second series, you replace this n with n minus 1. So here, okay, so you replace n with n plus 2. So here also replace n with n plus 2. And then here n minus 1 will be n plus 2 minus 1. Cn will be Cn plus 2. Xn minus 2 will be Xn plus 2 minus 2. Okay, minus. Okay, in this series, you replace n with n minus 1. So that's why we have n minus 1 here. And then Cn minus 1, Xn minus 1 plus 1. Okay, then we simplify all the terms. So for the first series, okay, n plus 2 equal to 2 now become n equal to 0 because plus 2, okay, and then you bring this to in the right hand side become minus 2. 2 minus 2 becomes 0. So n plus 2. So n plus 2 minus 1 will be n plus 1. So Cn plus 2. Xn plus 2 minus 2 will be x power of n. Then minus n minus 1 equal to 0 is equivalent to n equal to 1, because minus 1 you bring to the right hand side become positive 1, and then Cn minus 1, and then Xn minus 1 plus 1 will be x power of n equal to 0. Okay, now we have taken care of the power. The power are the same now, x power of n for both series, all right? But the problem is the index are not the same. Remember, we can combine the infinite series when the power are the same and the index are the same as well. Okay, so now we need to do something here. Okay, so now if we want to change the index, okay, the first one from 0 to 1, so that because so that both index will be the same. First, you replace the terms, okay, in the first series with n equal to 0. Okay, okay, now replace n with 0. We have 0 plus 2, which 0 plus 2, and is here n plus 1 will be 0 plus 1, because you replace this n with 0, and then C0 plus 2 x power of 0. From now on, okay, for the first series, we start in n equal to 1. Okay, from now on, in the first series, we start n with equal to 1. Okay, and then now both series have the same power and the same subscript or the same index. Okay. Same power, same index, and then we can combine these two. Okay, solve for this term. Okay, and then 0 plus 2 is equal to 2, 0 plus 1 is equal to 1, 2 times 1 is equal to 2, and then C0 plus 2 is equal to C2. Okay, x power of 0 equal to 1. So this term becomes 2C2. Okay, 2C2. And then for these two series, we can combine them together. Okay, you just write down their coefficient, which is n plus 2 times n plus 1 times Cn. Okay, and then minus, because the minus sign here, minus Cn minus 1. Okay, minus Cn minus 1 all together times x power of n. Okay, this one equal to 0. Okay, so all these terms will become 0 if and only if, okay, 2C2 equal to 0. Okay, 2C2 must equal to 0. And then this imply that C2 must equal to 0. Okay, 2C2 equal 0 imply that C2 equal to 0. And also, all the terms in this series must equal to 0 as well. Okay, meaning that n plus 2 times n plus 1 Cn minus 2 minus Cn minus 1 equal to 0. Okay, since now n we start with 1, so that means we write here for n equal to 1 through 2, 3, and so on. Okay, for this value of n depend on the index. Okay, we refer to the index. So for n equal to 1, 2, 3, and so on. Okay, from this we know that C2 is equal to 0, and then from these equations, okay, we want to express Cn plus 2 in terms of Cn minus 1. Okay, so Cn plus 2 is equal, you bring Cn minus 1 to minus Cn minus 1 to the right hand side, becomes Cn minus 1. And then this one, okay, n plus 2 times n plus 1. Okay, we bring to the right hand side. This one is multiplication, now become divisions. So Cn minus 1 divided by n plus 1 times n plus 1 for n equal to 1. Okay, n start with 1. And that's why here, okay, we start with when n equal to 1. Okay, when n equal to 1, C3, okay, here n equal to 1, that means 1 plus 2 is equal to C3. Okay, C3 equal to, okay, Cn minus 1, 1 minus 1 will be C naught, okay, over, okay, 1 plus 2, okay, 1 plus 2, and then here 1 plus 1 will be what? 3 times 2. Okay, 3 times 2 equal to 6. So C naught over 6. Okay, you have to find the coefficient the coefficient for few n, so that hopefully you can see some pattern here. When n equal to 2, so you plug into here n equal to 2, Cn plus 2 will be C2 plus 2 is equal to C4. And then Cn minus 1 will be C2 minus 1 will be C1. Replace this n with 2, 2 plus 2 times 2 plus 1, right? So you will get C1 over 4 times 2, 3 will be C1 over 12. Okay, for n equal to 3, okay, when n equal to 3, so this one 3, so Cn minus 1 will be C3 minus 1 will be C2, and then 3 times 2, 3 plus 2 times 3 times plus 1. Okay, now you have C2 over what? Over 20. But you know that C2 equal to 0. So this term is equal to 0 because C2 is equal to 0. Okay, from here C2 is equal to 0. So C now C5 equal to 0. When n equal to 4, C6 equal to C0 over 180. Okay, so you replace now n with 4. Okay, so you will get C3 over 4 plus 4 plus 1. Okay, that means 6 times 5 will be 60. But C3, okay, you have found C3. C3 equal to C0 over 6. So replace this C3 with C0 over 6. So now you have C0 over 6 times 30. That means C0 over 180. Okay. Similarly, for n equal to 5, we have C7. Okay, C7 equal to C4. Okay, because here we have okay, because n equal to 4, 4 minus 1 is equal to no, n equal to 5. Okay, 5 minus 1 equal to 4. Okay, 4, 5 plus 2, 7 times 6. But C4 is equal to C1 over 12. Okay, C1 over 12. Okay, over 42. That means 42 times 12 will be 504. So C1 will be C7 equal to C1 over 5 or 4. And when n equal to 6, okay, C6 equal to what? C8 equal to, okay, equal to, uh, um, okay, when n equal to 6, we have C8, replace n with 6 here, we have 6 plus 2, which is 8, here is 6, so becomes C5, but C5 equal to 0, okay, and that's why we have 0. And then I think we have see the pattern here, all right, see some pattern here. Okay, when n equal to 1, it depend on C naught. When okay, when we have C odd, when odd depend on C naught, when C even depend on C1, and then here when when C5 now becomes 0, okay, or 0. Okay, so we have C naught, C1, C2. When C2 0, this one will be 0, and then another one, okay, C5 0, and then C8 will become 0 as well. Okay, C5 0 and C6 0. So we go back to the forms, series solution form. So this is our form, right? So you expand this, so it will be C naught, C1x, C2x squared plus C3x squared, and then okay, C naught and C2 they are independent parameters. They remain unchanged. Okay, they remain unchanged because all other terms depend on C naught and C1. And then we know that C2 is equal to 0, just plug C2 equal to 0, and then C3 equal to C0 over 6x cubed, and then C4 will be C1 over 12x or 4, C5 will be 0, okay, and then C6 will be C0 over 180 x power of 6, and then C7 will be this, and then C8 will be 0. Okay, you just list the few terms. Okay, when to stop? I think when you have like when you substitute the value, it will go back to it make like a full of a circle. Okay, so now here you replace this and then you simplify. Okay, so all term depend on C0 and C1. Okay, so this one is C0, this one is C0, C0. So you take out C0. Okay, to get C0, you replace, you multiply this C0 with 1. Okay, to get C0 over 6 here, you replace C0 with 1 over 6 times x cubed. Okay, for this C0 over 180 x power of 6, you replace this with 1 over 180 times C0 x power of 6 and blah, 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 because it will go forever. And then the other terms involving C1. So this involves C1. You take out C1. To get C1x, you multiply C1 with x. Okay, to get C1 over 12x power of 4, you multiply, okay, you multiply C1 with 101 over 12, you get C1 12 over 12 x power of 4. Similarly, for this, you multiply C1 with 1 over 5 over 4 x power of 7. Okay, you cannot get like the general formula for this, so you just let be like that. Okay, we cannot see the general form as we did before. Okay, like here we can find the general form like this. Okay, but for this one we cannot find, so you just remain as it is. Okay, this one will be your solutions in terms of series. Okay, this is series, but you cannot write in terms of the general series. Okay, this is power series. This is power series. Okay, so we get this when we decided, okay, when we decided to change n x power of n minus 2, okay, and okay, we want to change it. We want to change xn minus 2 and xn power of plus 1 to x power of n. We want to change both power to x power of n. Okay, the question is, how about, okay, we change both x n minus 2 and x plus 1 to other power other than x power of n. Will we get the same answer? Okay, for example, if we want to change this to x power of n plus 1, will we get the same answer? Okay, will we get this? Okay, the answer is yes. Okay, so that's why I put here. Or for in this for this, okay, for this case, if we want to change, okay, both x power of n minus 2 and x plus and also x power of 1, if you want to change this, we want to change to xn plus 2 to the power of xn plus 1. So this one will remain unchanged. Because we want to only want to change this to x power of n plus 1. Okay, right now we change both power. But now we decide to only want to change this into xn plus 1. Okay, the answer will be the same. Okay, so we change xn minus 2. Okay, so that means if you want to change this power to n plus 1, we need to replace this n in the first series with n plus 3. Okay, so n plus 3 minus 1, sorry, this one, n plus 3 minus 2 will be n plus 1. So replace this n with n plus 3. So replace this, so we have n plus 3 equal to 2. Replace n with n plus 3. N minus 1 will be n plus 3 minus 1. Seeing n will be seeing n plus 3. Xn minus 2 will be n plus 3 minus 2. Okay, this one remain unchanged because we want to change the power to xn plus 1. Okay, now we simplify this. So now x plus 3 equal to 2, okay, will be n equal to minus 1. Because 2 minus 3 will be minus 1. Okay, and this will be n plus 3, this one will be n plus 2, and this one will be seeing n plus 3, then x power of n plus 1. Because n plus 3 minus 2 will be n plus 1, while the second series remain unchanged. Okay, remain unchanged. All right. Now, okay, all power are the same, but their index are not same. This one start with n minus 1, this one start with n equal to 0. Okay, so to make index the same, to make the index n equal to 1, first you replace this n with n minus 1. Okay, and then from now on, this n will start with 0. Okay, after you replace n equal to minus 1, then from now on, n start with 0. Okay, because when you add this minus 1 plus 1, we will get 0 there. Okay, so when you replace n equal to minus 1 here, you have minus 1 plus 3 times minus 1 plus 2. Okay, minus 1 plus 3 there, and then x minus 1 plus 1, because this n is equal to minus 1. Okay, and then this index now start with n equal to 0. Okay, again, this remain unchanged. We simplify this. Okay, minus 1 plus 3 is equal to 2. Minus 1 plus 2 equal to 1. Okay, so 2 times 1 is equal to 2. Minus 1 plus 3 equal to 2. So this one will be C2. So x minus 1 plus 1 will be x power of 0, which is equal to 1. Again, we will get 2C2 there. Okay, 2C2 there. Okay, but the terms inside this summation are not the same anymore. Okay, so now we can combine these two summations because both index are the power are the same. So this will be, okay, n plus 3 times n plus 1, seeing n plus 3. Okay, before this, seeing n plus 2, I think. Okay, before this, we have here seeing n plus 2. Now here we have seeing n plus 3. Okay, and then here, okay, we have Cn plus 3 and then minus Cn. Okay, before this minus Cn minus 1. Now becomes Cn. Okay, and then x power n plus 1. Okay, before this we have x power of n. Okay, but you do the same procedure. So all these will be 0 if and only if 2C2 equal to 0, which imply that C2 equal to 0. Okay, we have the same answer as before. And then you have to establish the relationship between Cn plus 3 and Cn. Okay, so Cn plus 3 equal to Cn over n plus 2, sorry, n plus 1, n plus 3 times n plus 2. So Cn plus 3 now equal to Cn over C over n plus 3 times n plus 2. Now from here, before this, n equal to what? N equal to 1. But from here, n equal to 0. We start with n equal to 0. 0, okay, 1, and then not 2, because when it's 2, now C2 equal to 0. That's why 2 is excluded. Okay, because when n equal to 2, oh no. No, this one I make some mistake. C equal to 2. Okay, 2 here become 5. This okay. 2 here there. Okay. Okay, now because this taken care of, C2 equal to 0. Okay, now from here, you start with n equal to 0. Okay, when n equal to 0, we have C3 equal to C0 over 0 plus 3 times times 0 plus 2, which is C0 over 3 times 2, C0 over 6. So C3 equal to C0 over 6. Compared to the previous one, okay, we get the same thing. Okay, C0 over C3 equal to C0 over 6. And then when you replace n equal to 1, you have C4 equal to C1. Okay, C1 over 1 plus 3 times 1 plus 2, which is, okay, so we have C1 over 12. Okay, you compare here, C4, the same thing, and then C5. Okay, C5 again here. Okay, we replace n equal to 2, we get C5. C5 equal to what? Equal to C2 over 5 times 4, which is 20. But C2 equal to 0. Then we have 0 here. Okay, the same thing that we have before. Okay, the same thing for C6, C7, C8, and so on. Okay, and the answer will be exactly the same as before. Okay, so the point is that it doesn't matter which power that you want to change to, the answer must be the same. The answer will be the same, although the terms here is different. Okay, although the term here is different from the previous one, but they are representing the same coefficients because the value of n here are changed as well. Okay, before this start with 1, now start with 0. So we will get the same coefficients. Okay, so we get the same answer at the end. Okay, any question before I move on? Any question? You can ask me now. Any questions? Okay, if no questions, then I will move on to example 7. Okay, find the first, okay, the keyword is find the first 4 non-zero terms. The first 4 non-zero terms in the power series expansion about x naught equal to 0 for the differential equation y double prime minus x square y prime plus y equal to 0. Okay, again, okay, so this is the general form of our series. okay, sin n times x minus x naught, summation of n from 0 up till infinity. But now since x naught is equal to 0, okay, now this term becomes x power of n. So x minus x naught power of n now become x power of n because x naught be equal to 0 now. Okay, again, we need to differentiate once to find y prime and twice to find y double prime. So y prime again is equal to n sin nx minus 1, while y double prime equal to n times n minus 1 sin nx n minus 2. Now n become start with 1, now n start with 2. So you use the same process as before. You substitute y double prime with this summation, and then y prime with this summation, and y with this summation. Okay, now we get this. The first step, okay, since this one is y double prime minus x square y primes, okay, and then plus y, okay, equal to 0, okay, equal to 0. So since we have x squared there, we have to bring this x squared inside these summations. Okay, so we have, okay, x squared times xn minus 1. Okay, so we get xn plus 2. Okay, because this will be xn minus 1 plus 2 will be n plus 1. Okay, so now we have to decide. Okay, we have to decide, okay, we want to change this n plus xn minus 2, xn plus 1, and x power of n to which power? Okay, in the example here, I change this n plus 2 and xn to n plus 1. Okay, so the second series remain unchanged. We only change the first and the third series. Okay, you can change this n minus 2 xn minus n plus 1 to xn as well. Okay, you will get the same answer as I described earlier. All right, so if I want to change this xn minus 2 to xn plus 1, this n in the first series must be replaced with n plus 3. So this one will be n plus 3 equal to 2, n plus 3 here, and then n minus 1 will be n plus 3 minus 1. Cn will be Cn plus 3. Now xn plus 2 minus 2 will be xn plus 3 minus 2. This one remain unchanged. For the third summation, replace this n with what? N plus 1. Because we want to change this to n plus 1. So n plus 1 equal to 0. Cn will be Cn plus 1. And then this xn will be xn plus 1. Okay, and when we simplify this, now n start with for the first series, n start with minus 1. Okay, and then this will be n plus 1. This one will be n plus 2 because n plus 3 minus 1 is n plus 2. And then this one will be Cn plus 3. So now now it becomes xn plus 1. Okay, xn plus 1. This one remain unchanged. Okay, the third summation will be n from minus 1. Okay, because 0 minus 1 will be minus 1. Cn plus 1 and then xn plus 1 is equal to 0. Now all the power in these three summation are the same, which is x power of n plus 1. All right. The problem now is the index. Okay, index. In the first summation, index start with minus 1. In the second summation, n start with 1. Whereas in the third summation, n start with minus 1. All right. So the next step, I want to change this. Okay, I want to change this index with 1. The first in the first summation, I want to start n with 1. So is in the third term summation, I want this n start with 1 as well. Okay, now replacing this n with equal to minus 1, I get this minus 1 plus 3 minus 1 plus 2, c minus 1 plus 3, x minus 1 plus 1, and then I need to replace this with 0 as well. Okay, when n is 0, we have 0 plus 3, 0 plus 2, c 0 plus 3, x 0 plus 1. Then from now on, the index will becomes 1. Replace here with minus 1, 0, and then from now on, the index for summation is equal to 1. Start with 1. Okay, this one remain unchanged. Similarly, for the third summation, okay, we replace n with minus 1. We get minus 1 plus 1 x and minus 1, x minus 1 plus 1. And then again, we replace this value with 0. So we have c0 plus 1. So x0 plus 1. And then from now on, the third series will begin at n equal to 1. Okay. And then the next step, we simplify all the terms here. Okay, minus 1 plus 2 plus 3 will be 2. Okay, 2 plus this one minus 1 plus 2 will be 1. Okay, then 2 times 1 is equal to 2. C minus 1 plus C will be C2. Here 0 plus 3 is equal to 3. 3 times 0 plus 2 is equal to 2. 3 times 2 equal to 6. And 0 plus 3 is equal to 3. So this one will be C3. X power of 0 plus 1 will be X. Okay. The first term you got 2C2. And the second terms for the first summation we get 6C3X. Okay. And now this remain unchanged. Now for this term, because C minus 1 plus 1 will be C naught. Okay, x minus 1 plus 1 will be x naught. X naught is equal to 0. So, equal to 1. So 1 times C naught. So we have C naught. For this term, it reduced to C1 times x. And this one remain unchanged. Okay, and if you observe for all three summation, the power are the same. Okay, the power are the same, which is xn plus 1. Okay, and the index are also the same. We start with n equal to 1, n equal to 1, and n equal to 1. Okay, and then we can combine all these summation. So we bring these terms. Okay, now we compare this. You have 2C2 plus 6C3X. And here C0 plus C1X. Okay, here we have all the constant. Okay, all the constants 2C2 okay, plus C0. So you combine the constant terms. So C0 plus 2C2. And then for these two terms, 6C3X and then C1X. So this is, we have like the coefficient for X. Okay, so we combine these two as well. So we have C1 plus C6C3 times X. Okay, so we combine this, and then now we have to combine all the summations. Okay, summation. Okay, and then take the coefficient for the first summation. So n plus 3 times n plus 2 Cn. And then minus the second summation is what? The second coefficient is what? N Cn. Okay, N Cn. And then for the third series, the coefficient is Cn plus 1. So plus there, that's why plus Cn plus 1. Okay, all these coefficients you times with xn plus 1. Okay, and equal to 0 using the same approach or procedure as before. From here, we have C0 plus 2C2 must equal to 0. Okay, from these terms, okay, we conclude that C0 plus 2C2 must equal to 0. And this implies that C2 equal to minus C0 over 2. Okay, from these terms, okay, we have C1 plus 6C3 equal to 0. Okay, this implies that C3 equal to minus C1 over 6. Okay, and then from this summation, all the terms, all the coefficient must equal to 0 as well. That means n plus 3 times n plus 2 Cn plus 3, okay, minus n Cn plus Cn plus 1 must equal to 0. Now you want to express Cn plus 3 in terms of Cn and Cn plus 1, right? So we will get Cn plus 3 is equal to, this one become minus become plus because we cross the right and we cross the equal sign. Okay, this one will be n Cn, this one will be negative Cn plus 1. This one multiplication become divisions, n plus 3 times n plus 2, and start with 1. Because based on this, n start with 1, okay, and then 2 and so on. Okay, so this is the relationship between Cn plus 3 and Cn and Cn plus 1. Again, substitute with n equal to 1. When n equal to 1, we have C4. C4, okay, 1 here. 1 plus 3 equal to C4. C4 will be what? This one, 1 C1. So we have C1. Then minus 1 plus 1 will be minus C2 over, okay, 1 plus 3 is equal to 4. 4 times 3 equal to 12. So we have C4 equal to C1 minus C2 over 12. Okay, that's it, 12. All right, we are asked to find the first four non-zero terms. So I will stop up to here. Okay, no need to do further because we are asked to find only the first four non-zero terms, right? So y equal to, okay, our solution will be in this form, right? So y equal to C0 plus C1x plus C2x squared plus C3x cubed, so on. So I replace this, okay, C0 and C1 are independent variable. I mean, it remain as it is. Okay, they are independent. And then C2 now equal to, okay, C2 equal to minus C0 over 2. Okay, that's why we have here. Okay, C2 replace with C0 minus C0 over 2. And then C3 is equal to, from here, C3 is equal to minus 1 over 6. So replace this C3 with minus, okay, minus C1 over 6. So this is non-zero, these four non-zero terms. Okay, if, for example, if C0 is equal to 0, then you have to list down all non-zero term. Okay, because C0 now equals to is not counted because 0. But the question, you refer to the questions, you have to find the first four non-zero terms. Okay, so in this case we have this, and let's say, for example, if C0 equal to 0, then you have to add another terms here. Okay, because you are asked to find four non-zero terms. Okay, so this is four non-zero terms. Any question before I proceed? Okay, the concepts are the same. Okay, I explain one time, the concepts are the same. Okay, here, okay, the first step, okay, you write down the representation of the solution in term in series. So this is general form. This one, this first, this. Okay. Okay, now this x0 depend on this value. Okay, for example 7, x0 equal to 0, and that's why x minus x0 become x power of n. But it's not always like this. Okay, it depends on the value of x0. Okay, so now you find this, and then you need to find, okay, based on the given equation, you need to find y prime and y double prime as well. So you differentiate y, we get y prime. you get y, you differentiate y prime, you get y double prime. Of course, in terms of series. And then you plug y double prime, y prime, and y in terms of series. And then you need to simplify this. Okay, in here we have x squared. You got to bring x squared inside because x squared is what? It's not a constant. It is okay. You have, in fact, you have to whatever in outside of summation, whatever in terms outside of summation, you got to bring them inside. Okay, so that then you can combine. Okay, so that we can combine, providing that all the powers and also all the index are the same. So in this case, we cannot combine because the power are not the same. So are the index. They are not the same, right? So first we have to change the index, okay, to make them the same. So you have to decide now. There is no specific way, okay? How there is no like unique way to make this. So it's up to you. It's up to you. Okay, as long as the power are the same. Okay, here we convert to n plus 1. Okay, and then again, okay, and then now the power remain the same. Now the index are the same. You have to change the index to make them the same, and then you have to like substitute. Okay, this n is minus 1 and 1 and 0, and now the index becomes 1. Okay, the same you do for the third summations. Replace the n with minus 1 and 0, and from now on, okay, the index will be 1. The rest you just simplify, and all coefficient must be equal to 0. That's why you have this value here, and the index and also the coefficient inside the summation must also be equal to 0, and the value of n here depend on the index. Okay, and then you list few terms, and then you will get the solutions. Okay, that is the basic concept. Okay, again, it depends on x naught. Okay, if x naught equal to 0, you have x power of n. If not, then you have to put x minus x naught to the power of n. Okay, so this is okay. So here we are only consider x naught is what? Is ordinary points. Okay, x naught is ordinary points. So in the next slide, okay, in this slide, okay, we're talking about, we want to find series solution around singular point. Okay, before this, ordinary points. Now around singular point. Okay, so in order to do that, okay, first, okay, we refer to equation number 1. Okay, again, this is linear second order, okay, homogeneous. Okay, linear second order ODE, homogeneous ODE. Okay, we have done before. We have to change the coefficient of y double prime to be 1. So we divide all terms with px. Okay, this one capital P. Okay, capital Px. This one capital Q, capital R. Okay, before this we have A1, A2. Because before this we have A1, this one A2, A1, A0. Now we use, this is just a matter of notation. Okay, we use P0, okay, P, Q, and R, and then we, okay, and then in order to make the equation of the y double prime equal to 1, we divide all terms with capital Px. So now reduce to d square y dx square. Okay, px dy dx. This one become qx y equal to 0. Okay, where p small px This one small px equal to capital Qx over capital Px. And then this Qx equal to capital Rx over capital Px. Okay, before this we have A1 over A2, A0 over A2. Now we have Qx over Px capital and then Rx over Px capital. Okay, again, okay, then the singular point, the singular points for the equation 1 are what? Are those points where capital Px equal to 0, right? The same thing as before. Before we have A2, now we have capital Px equal to 0. Okay, there are few terms here that you need to know. Okay, now we have, okay, types of singular points. Okay, we're talking about singular points. Okay, there are types. Now we will learn the types of singular points. Okay, there are two types of singular points. Okay, the first one is called regular singular points. Okay, there are two types of singular points. The first one is known as regular singular point. The other one is irregular singular points. Okay, we have regular singular points and irregular singular points. Okay, let's go to the first type, which is regular singular points. Okay, regular singular point. Okay, now let x naught be a singular point. Okay, in the previous section, x naught is what? Is ordinary point. But in this section, x naught is what? A singular point. All right. Now, in order to determine the order of the types of singular points, okay, first we need to construct these functions. Okay, x minus x naught times px. This one is small px, not capital. Okay, and also x minus x naught square qx. Okay, this one again small q. Okay, so we need to construct these two functions, x minus x naught px and then x minus x naught square qx. Okay, so if both functions are analytic, okay, what you mean by analytics? I mean all value the value of the function is defined at x naught. Okay, the value we have the value of the function at x naught. That means that is what we mean by analytic. Okay, the key word here, if the function, if the function x minus x naught times px and x minus x naught square qx are both analytic, they both are analytic, x naught, then x naught is called regular singular point. Okay, if both are analytic at x naught, then x naught is called regular singular point. Okay, if either one of them is not analytic, okay, then it's called irregular singular point. Okay, so the point x equal to x naught is called an irregular singular point if one or both, I mean at least one or both of the function, this function is not analytic at x naught. Okay, regular if both. If one of them is not analytic, that is called irregular singular point. Okay, so example 8. Identify the types of singular point if exists. Okay, if the singular point exists. If the singular point exists, then you need to identify the types of singular points. Okay, so example A, okay, 1 plus x y double primes plus 2xy primes minus 3y equal to 0. The first step, we want to eliminate this 1 plus x. So we divide all terms with 1 plus x. So this will be y double prime plus 2x over y 1 plus x y primes, okay, minus 3 over 1 plus x y equals 0. So this is your capital P. Okay, capital P. Okay, this is capital Q. Capital Q, I think. Yes, capital Q. And this is what this will be your capital R. But that is not important. You have to. The most important is that you reduce to this, and the whole thing here, the coefficient in front of y prime will be small px. The coefficient in front of y will be small qx. This one is small px with the positive sign. Okay, here small px. This one will be small qx. Okay, and then okay, what are the singular points? What is a singular point? Okay, we just focus on denominator. Okay, they have the same denominator, which is 1 plus x. So plus, okay, 1 plus x equal to 0. So that means x equal to minus 1. Okay, when x equal to minus 1, okay, this px and okay, this will be undefined. Okay, when x equal to minus 1, okay, these both of px and qx will be undefined. Okay, and that's why x naught equal to minus 1 is a singular point. Okay, so we get the singular point. The next step, we want to determine the type of this singular point. Is it regular? Is it irregular? Okay, is it regular or is it irregular? Okay, so to do that, okay, first we need to construct this function. Okay, x minus x naught times px. Okay, x minus x naught times px. Now x naught now equal to minus 1. So x minus x naught will be x minus minus 1. So we get x plus 1. Okay, x plus 1 times px. Px equal to 2x. Okay, 2x, okay, over 1 plus x. Okay, 2x over 1 plus x. And then we simplify this x plus 1 and plus 1. We can cancel these two. So we will get 2x. Okay, we got 2x. Okay, now for x minus x naught square qx, again, we replace x naught with x with minus 1. So we have x minus minus 1, x plus 1 square. So qx is equal to minus 3 over 1 plus x. Okay, so replace with this. Okay, minus 3 over 1 plus x. Again, we can cancel this and x plus 1 square. So x plus 1 square divided by 1 plus x. Okay, 1 plus x is equal to 1. X plus 1 is equal to 1 plus x. They are the same. So you just arrange the order. So this one is power 1, this is power 2. So it will reduce to x plus 1. Okay, x plus 1 times minus 3. Okay, remember this and this cancel. We will get x plus 1, power of 1, and then multiply by minus 3. We have minus 3 times x plus 1. All right. And then if we substitute the value of x naught here with minus 1, so we have 2 times minus 1. So that we will get the value of minus 2. So we get the value. Okay. Then here also, when we replace x with minus 1, so we have minus 1 plus 1 is 0. So 0 times minus 3 is 0. So that we have, so the function both function, we get some value here. So that means both functions are defined. Both functions are defined, okay, at x x not equal to -1, okay, meaning that both functions are analytic. Again, I explain one more time. Okay, after simplifying this function, both function, so you will get that x minus x naught times px equal to 2x, and then x minus x naught square qx, it becomes -3 times x plus 1. And then if we substitute this x with the singular point, which is -1, so we get -2 there. And then while in the second function, we will get -1 plus 1, which is 0, minus times -6 is equal to 0. So we have value. Okay, both functions are defined at x naught. Okay, when both functions are defined, these imply that both functions are analytic. Okay, so that means both functions are analytic x naught equal to -1, and then that's why x naught is equal to -1 is what? A regular singular. Okay, regular singular. Okay, so you will try B. Try yourself to do B. Okay, for B also, probably I'll try this one. Okay, I will try this one. Okay, for B, again, we want to find a singular point. So we have to eliminate this x squared times 1 minus x squared. We want to eliminate these terms. So now we divide all terms with x squared times 1 minus x squared. So we get this. Okay, we got these terms. Okay, so this will be your px. Okay, this will be your px. This will be your qx. Okay, small px, small qx, this. Okay, and then we look at the denominator. Okay, they are the same. And then this will be 0. Okay, the value that make the denominator is equal to is 0 is we call it what? Singular point. Okay, so x squared times 1 minus x squared equal to 0 if and only if when x equal to 0 or when x equal to 1. Okay, x squared times 1 minus x squared is equal to 0 if and only if x equal to 0 or x equal to 1. Meaning that we have two singular points. Okay, we have two singular points. Okay, so next we need to determine the types of this singular point when x equal to 0 and also when x equal to 1. Okay, let's begin with x not equal to 0. Okay, when x not equal to 0, then x minus x naught times px will be x minus, okay, times px. This is your px. Okay, and then simplify this. Okay, x times x will give what? X squared. X times x give you x squared. X squared and this x squared can be cancelled out. Okay, so we have 4 minus x squared divided by 1 minus x squared. Okay, and then whereas in the second function, x minus x naught cube square, okay, times qx, okay, equal to x. Okay, you replace this x naught with equal to 0. So and that's why you have x equal to x minus 0, which is x squared. The same thing here because x naught is equal to 0 there, right? So we have x squared times qx. Qx is 2 plus 3x over x squared times 1 minus x squared. This one, the whole thing square. And then this x naught and x squared and x squared cancel out. So we have 2 plus 3x over 1 minus x squared. Okay, now to determine whether it's regular or irregular, so we replace x equal to 0 here. So 1 minus 0 is equal to 1. Okay, and then 4 minus 0 is equal to 4. Okay, 4 over 1 is equal to 1. So we have some value here, which is equal to 4. The same thing here, replace x with 0. We have 2 plus 0 over 1 minus 0 with 2. Okay, so since these two functions have value here, are defined, both are defined at when at x equal to 0. That means x equal to 0, x not equal to 0 is what? Is regular singular. Okay, is regular singular because both functions are defined at x not equal to 0. Okay, now let's consider x not equal to 1 because we have found two singular point. When x 0, we can conclude that this singular point x not equal 0 is what? Is regular singular. So for x equal to 1, the same thing here, we construct this, the same thing, except now we replace this x naught with 1. Okay, before we replace this x naught equal to 0. Now, in the second case, we replace x naught equal to 1. Okay, now we replace this. Okay, and then we simplify. Okay, this one x minus 1. And then this one is 1 minus x. Okay, we can simplify this. Okay, because in the square we can simplify this. Also x and x squared, we have x. And then this and this. Okay, here we can write down as, okay, let me see like this. Okay, so this one be equal to minus. Okay, minus, this one will become, okay, 1 minus x. Okay, so this one will be minus there. Okay, so I can express x minus 1 as minus, okay, 1 minus 1 plus x. Okay, they are the same. X minus 1 equal to minus 1 minus x. Okay, and then I can cancel this 1 minus x and this 1 minus x squared. So I will get here, like this. Okay. Okay. Okay, so here, okay, so this, and then when you replace x with 1 here, you have x times x minus 1. Okay, 1 minus 1. Okay, that means 1 times 1 minus 1, but you have 0. Okay, your denominator will be 0. So 0, that means this function is undefined when x equal to 0. When it's not undefined, when it's undefined, that means the function is not analytic. Undefined is equivalent to not analytic. So the function is not analytic. Okay, when x equal to 1, so you don't have to do this. Okay, you don't have to do this. Okay, one is not analytic, then you can conclude that, okay, this when x not equal to 1 is irregular singular point. Because at least one, if one of them is not analytic, you can conclude that the singular point is irregular. So x not equal to 1 is irregular singular point. X not is what? Is regular singular point. Okay, while x not equal to 1 is irregular singular point. Okay, in the next meeting, okay, which is on Thursday, we will find, okay, this series solution around regular singular point. Okay, around regular singular point. Okay, the method is called Frobenius method. Okay, Frobenius method. Okay, Frobenius method can be used to find series solution if and only if the singular point is regular. Okay, if the singular point is irregular, we cannot use Frobenius method to solve, okay, this to find the series solution. Okay, but in this class we will focus on a regular singular point. Okay, so we can apply Frobenius method. Okay, for irregular singular method we won't discuss in this class. Okay, there is an advanced ODE. Okay, so I think that's all for today. Okay, thank you for your time.